First speaker today will be Liling Sun. And please, Liling, take it away.
Okay, thank you. First of all, I would like to thank the organizer for inviting me to this workshop. I'm Liling Sun from Institute of Physics, Chinese Academy of Sciences. The title of my talk today is Evidence of Filamentary Superconductivity in Pressurized La3 Nickel-2 Oxygen 7 single crystals. So last year, Professor Wang's group reports the significance of superconductivity near 70 Kelvin in a nucleate under high pressure. So this discovery attracts a lot of attentions in the community. In particular from the theoretical side. So you can see that many papers got published from the theoretical side. Up till now, I think more than 50 papers got published. On the experimental side, although the publication number is less than that of the theoretical paper, but some true progress has been made, actually. And in this talk, I will mainly introduce the transport property under high pressure. So here is the results from Professor Jingguang Chen's group. They did the resistance measurement on the 3 to 7 single crystals provided by Professor Wang's group. They find the resistance, zero resistance state under the hydrostatic pressure condition in some samples. And later on, Professor Hui-Qiu Yuan's group also finds a zero resistance state under hydrostatic pressure condition in some samples. Professor Bob Kava's group grow their own 3 to 7 single crystals with large oxygen vacancies, say about 0.5, and they didn't see the superconducting transition in their sample under high pressure up to 41 GPa. Instead, the sample displays a semiconducting behavior at this pressure. Professor Wei Xi's group did the chemical dope, did the strontium doped on the lanthanum side, and did the high pressure resistance measurement on their sample, and find that no evidence of the superconducting transition is observed under pressure up to 19 GPa. So some progress has been made to synthesize a polycrystalline sample. Professor Jingguang Chen's group synthesized the polycrystal sample by using show gel method. They find that the powder sample display a superconducting transition with a zero resistance state at about 13 GPa. And Professor Yan Pengqi's group synthesized the powder sample through the method of the solid state reaction. The resistance drop is observed at 29 GPa, but there is a resistance uptrend at the low temperature. So you can see that different samples display different behavior under high pressure. And these samples are not reproducible in their measurement. So we decided to do the high pressure AC susceptibility measurement on the single crystals to see what the superconducting volume looks like. Before the high pressure measurement, we did the ambient pressure characterization of the single crystal 3 to 7 samples, which provided by Professor Wang's group. We did the single crystal X-ray diffraction patterns, and the sample, you can see that the sample crystallized in let's see, I move this. In the AMMA phase, we also did the EDAX study and find that the ratio of the lanthanum and the nickel is about 3 to 2, so indicating that this is the bilayer material. We did the resistance measurement at ambient pressure and find that the sample displays the metallic behavior at the ambient pressure consistent with the result reported. So we first performed the AC susceptibility measurement on the sample through a single phase locked amplifier. And here's our experimental setup. The signal to noise ratio of the system is about 5 to 1, implying that if the superconducting volume is less than 20%, the superconducting diamagnetic signal cannot be detected. And here is the our raw data of the AC susceptibility versus temperature obtained at different pressures. You can see that at 2 GPa, the susceptibility versus temperature shows a dip-like behavior. You know that at this pressure, the sample is not superconducting at all. So the dip-like signal is the background signal. So we find that in the whole experiment pressure range, the sample shows the same background signal, indicating that no superconducting transition occurs up to 40 GPa. So only the background signal can be found, indicating that the superconducting volume of the nickel 3 to 7 is less than 20%. And then we apply the new technique to study the superconducting volume on the 3 to 7 single crystals. And here is our new experimental setup. The signal to noise ratio of this new system is about 115 to 1. So implies that if the superconducting volume is less than 0.8%, the superconducting diamagnetic signal cannot be detected. So in this measurement, we load the superconducting vanadium in the same sample chamber as a reference, which allow us to determine the superconducting volume more precisely. So we start the measurement at 8 GPa. So you can see this is the AC susceptibility versus temperature. You can see the hump-like signal. So from our resistance measurement, we know that at 8 GPa, the sample is not superconducting. So the hump-like signal is the background signal. We increasing pressure from 8 GPa to 22 GPa, and we find a new broad peak appears based on the background signal. So this new peak is associated with the superconducting diamagnetic signal. So we increase the pressure up to 28 GPa and find the height of the new peak is decreased, suggesting that the superconducting volume is decreased upon increasing pressure. And then we decrease the pressure from 28 GPa down to 17 GPa and find the superconducting transition disappear at 17 GPa. Then we compare the peak heights of the 327 sample with that of the vanadium, and find that the maximum superconducting volume of the 327 single crystal is about 1% at 22 GPa. So this small superconducting volume suggests that the observed superconductivity of the 327 sample is not bulk. We repeat the measurement on the other 3 single crystals. No superconducting diamagnetic signal is observed, indicating that the superconducting volume in these 3 samples is less than 0.8%. We also did the resistance measurement on the 327 samples. And here is the resistance versus temperature at different pressure for 3 independent runs. So we observe the resistance drop for these samples, but no zero resistance was found. We did more resistance on the sample. Here is the results of run 4 and run 5. In the measurement of run 4, we find that the sample display semiconducting-like behavior below 8 GPa. However, it shows a resistance drop at 11 GPa. The drop becomes pronounced upon increasing pressure and approaches 0 at 19 GPa. In the run 5 measurement, we find the zero resistance state at 17 GPa, and the zero resistance states persist up to 31 GPa. Then we release the pressure from 31 down to 0.5 GPa, and we find that the pressure induced the transition from semiconducting state to superconducting state is reversible. So based on our AC susceptibility and the zero resistance measurement, we proposed that the superconductivity of the nickel 321 single crystal is filamentary-like. Because this kind of the superconductivity has the following features with very weak Meissner effect. The presence of the resistance drop without reaching zero resistance. The presence of the zero resistance state, but with poor reproducibility. The question is, why does a single crystal house the filamentary-like superconductivity in these samples? I think the main reason is that the sample is inhomogeneous. So recently, Professor John Mitchell's group grown their own nickel 327 single crystal and did the careful characterization on their sample. They find that the single crystal contain different stacking phases, including bilayer phases, so-called 2222, and monolayers and trilayer phases, so-called 1313 phases. And Professor Haptin's group also grown their own nickel 327 single crystals. And they find multi-phases in their sample. Interestingly, they find the superconducting behavior in the 3 phases at 11 GPa. And significantly, they find the evidence of filamentary superconducting behavior in this sample. So the question raised, is the 1313 phase is the superconducting host phase? I think it deserves further investigation from theoretical and experimental size. So we also did the whole measurement on the 3 to 7 single crystals. And here is the results of hole resistance versus field obtained at different pressures. We find that the hole resistance remain positive over the pressure range from 3 GPa to 29 GPa. So suggesting that the whole carrier is dominated. We extract the whole coefficient based on our experimental results and plot it as a function of pressure. So we find that the whole coefficient display a dramatic change at the critical pressure where the superconducting transition emerges. So these results indicating that the reconstruction of electronic structure plays a role for boosting the superconducting transition. Summary. We confirmed the existence of the superconductivity in nickel 3 to 7 single crystals through the measurement of zero resistance and the Meissner effect. We find the superconducting volume of the single crystal is about 1%, suggesting that the superconductivity of the nickel 3 to 7 is filamentary-like. We also find that the whole coefficient display a dramatic change at the critical pressure where the superconducting transition occurs. Here, I would like to finish my talk using this slide. Professor Dicto raised some question on the nickel 3 to 7 sample in their paper. So we think our experimental result may answer these questions. His first question is, why observe the TC in the superconducting pressure doesn't change much instead of the superconducting dome? Now our answer is, in this pressure range, the superconductivity is filamentary-like. TC of the filamentary superconducting phase is not sensitive to the pressure-induced volume shrinkage. Second question, are the structure or pressure itself important for superconductivity? The answer is the pressure-induced structure phase transition play a crucial role in developing the superconductivity. The third question is, does the Fermi surface topology and the wave pairing symmetry change in the FMM phase under high pressure? Now, our answer is, from our experiment Hall measurement, we find a large drop in the Hall coefficient, which suggests the occurrence of the Fermi surface reconstruction during the transition. The Hall coefficient versus pressure changes slightly in the high pressure phase, suggesting that the topology of the Fermi surface in this phase doesn't change much upon increasing pressure. The fourth question is, what are the mean difference between lanthanum, nickel, oxygen, and bismuth cuprate? So we think that the distinction is that the former is a pressure-induced filamentary-like superconducting system, while the latter is the ambient pressure bulk superconductor. The common characteristic shared by these two superconducting oxides is that the superconducting transition is reversible. So finally, I would like to thank our collaborators. We would like to thank Professor Wang and Professor Xun for providing us the single crystal samples. I also would like to thank my colleagues, Professor Tao Xiang, Qi Wu, and Jing Guo, Doctors Yazhou Zhou and Shu Chai, for their important contribution to these works. Special thanks to Professor Dao Mao and Yang Ding for useful discussions. I thank you for your attention.
Thanks a lot, Liling, for a beautiful talk. I really found the Hall data to be very impressive. It indicates that most of the Fermi surfaces actually remove the density wave transition. So that's really very interesting. A comment about this volume fraction being all over the place. I'm wondering, with the 4,310 materials, those samples seem to be more pristine than the 327. So it'll be interesting to see what the volume fraction of these 4,310 materials are. Maybe the superconducting volume fraction will be a lot more.
Yes, that's true. Yeah, it has reported recently by Jun Zhao's group. They find zero resistance behavior and the large superconducting volume in their samples. That's true.
Right. So any questions from the audience? Jimiao?
Yeah,
yeah.
So I also want to follow up on this Hall coefficient showing jump-like behavior. Just empirically, is there some other quantity which is what are they doing? For example, rho XX, does it also jump?
Yeah, rho XY actually we measured. That's the has been characterized by a reference example. Is really a Hall resistance of from
Can you see what the longitudinal resistivity is doing? Is it showing similar?
Yes, that's right. Yeah. So for the Hall measurement, we can still monitor the resistance versus temperature at different pressures. We also observe the resistance drop. Yeah.
Okay,
from this sample.
Very interesting.
Really interesting. Any Any more questions? So, do you think, Liling, that the small in volume fraction of the 327 could be that the superconducting phase has a particular oxygen stoichiometry? It seems like these results are very sensitive to oxygen stoichiometry in the 327.
Yeah, I agree with you. The oxygen vacancy is quite seriously affected to the property, superconducting property. So the different amount of the oxygen vacancy and different distribution will affect the superconducting behavior, I think. So recently we did some investigation on the oxygen vacancy versus TC, and we find some evidence about that. So this project is still under doing. So I didn't report our results here.
Very good. Any more?
Oh, Mike, can I raise a question?
Sure,
Sure,
absolutely.
Haihu, yeah.
Yeah. So from the phase diagram from different groups, it looks quite similar. So it seems that once the system go to the FMMM state, that phase, then the superconductivity comes in. But although the volume is small, so that's something puzzling. On one hand, the phase diagram shows some commonality, but the superconductivity volume is still small. So that's something I don't understand. Can you? That's also a question you list.
Yes, that's true. And the recent high pressure, low temperature X-ray diffraction measurement indicated that the superconducting phase has the tetragonal phase. It's not FMMM. That's I4MM phase. So that's a big question for this material. Why is the superconducting volume is so low? Is it related to interface superconductivity or surface superconductivity? We don't know. It calls for further investigation. But it's really an interesting physics. Interesting material. I mean, there are many physics behind, so we need more investigations.
Yeah, sure. Okay, thank you.
Thank you. So could you stop sharing your screen and then let Haihu share his screen, and then while you're doing that, Chimiao has a final.
Yeah, so it's actually maybe a question for Harold as well. So I thought the infinite layer Nicolate, the Hall coefficient, well, there were some sign changes, but if I ignore that, it looked to me that there was also some jump-like feature as a function of doping concentration. Is that fair?
So in the interest of time, I probably have to think and look at it. So I don't think it's a stark discontinuous jump. As a function of what temperature you would take this slice, there would be kind of more steepness to it. But I don't know that there would be something equivalently sharp.
Right, but there is a large magnitude jump, and this is because these 5D pockets are small, and then when the large hole surface comes into play, then the magnitude of the Hall goes down significantly. So
I mean, maybe the origins are different, but nonetheless, superficially, I wonder what's the degree of similarity or dissimilarity there. Yes.